This is on chemistry by Julia Weinstein from the University of Sheffield. Julia, welcome.
Magically appearing.
Sorry, just waiting for the
Okay. Well, they'll give me extra minute, right?
Yeah.
No. I did have some prepared. It does show my own. So my first joke was, that's how we looked like when we started. So thanks very much, Ian. And it's a fantastic opportunity to talk about what we could potentially do with free electron lasers in chemistry. Of course, huge thanks to Andrew, Sophia, Russell, Tom, and a lot of collaborators all over the world, including lots of collaborators from XFELs to help us put the case together. And from the chemical sciences point of view, I'm not going to be talking so much about the capability, but more about the science question. What are the questions we want to be answered? So if you look at chemistry, you got a lot of dynamics. You have charge transfer dynamics in catalysis and light harvesting. You have spin dynamics in, for example, single molecule magnets. You have dynamics of electronic coherence and how you can probe it potentially with attosecond X-ray Raman. You can also look at somewhat more applied aspects, such as exciton dynamics in photovoltaics. And you can also look at very fundamental chemistry question, solvent-solute interaction dynamics. You can move further again into applications, and that will give you plasmonic photocatalysis or all sorts of photocatalysis. So what we need for all of this is simultaneous measurement of electronic spin and structural dynamics. And it needs to start from femtoseconds or even faster maybe. And then we can answer this question, which X-ray crystallography has been answering for quite some time. So we want to answer these questions in solution, at the interface, in gas phase, in solids. So some more examples here. So gas solution and solid. This is an absolute archetypal molecule because this is a famous ruthenium N3 dye, which is used in dye-sensitized solar cells. So if we look at this molecule, it's been used by probably millions of scientists for various purposes. But do we really know dynamics, structure, and redox events in it? And do we really know how this is related to the performance of solar cells? So we need to look at electronic vibration and vibronic coherence. And we really need to look at multidimensional, ultra-fast photochemical reactions. We need to understand the reaction coordinates. It's a very fundamental question for everything in chemistry. Where do X-rays come in? Well, I would like to be able to measure changes on all of those atoms: ruthenium, nitrogen, carbon, sulfur, oxygen, at the same time. And I would like to measure electronic changes, structural changes, and spin changes. So for that, we need high repetition rate, and we need synchronization of X-ray and optical pumping, which is probably obvious to everyone in this room. But it's really important that we have high rep rate to be able to collect sufficient signal to noise, for example, and we need femtosecond pulses. So if we move to clusters and macromolecules, then you have correlated spin vibronic dynamics, those single molecule magnets I mentioned on the previous slide. So you have manganese, oxygen, and carbon. Again, want to look at all these atoms and what is happening to electronic spin and structure. And that brings me to a really important part here. We'd like to be able to have simultaneous multiple detection methods, X-ray absorption, X-ray emission, various types of scattering, and we really need simultaneous detection from light and heavy elements. And if I move now to even more complex systems, which would be materials and devices, then you can look at terahertz-driven reactions. For example, you have phonon-up conversion and metal oxides, or some other applications I'll show in a little while, where you have a crystal and you need to look at what is happening at every atom in this crystal. And that brings me to another aspect, not only probing, but excitation, where you want to have infrared or terahertz excitation and detection so that we can access low energy reaction coordinates. And we also need a lot of ancillary infrastructure, fully tunable excitation sources. I think quite a lot of people who go to XFEL have this limitation of not being able to access exactly excitation wavelengths we want. So it's really important that the whole range of excitations is available. And of course, sample delivery and detectors, Alan's already mentioning this. So ultrafast spin electron structural dynamics in one experiment. An example here is a beautiful RIG study of a workhorse of inorganic photochemistry, iron pentacarbonyl. So here, what was done by using time-resolved resonant inelastic X-ray scattering, it was possible to probe the frontier orbitals, and it was also possible to resolve the intimate steps of dissociation of the ligand and what is really happening in this molecule. If you would like, it's a chemical atom, right? So if we talk about molecular movies and watching chemistry happen, then the movie part here is ligand dissociation, and that's of course primary steps in catalysis. Then the application parts, which are really important, of course, would be related to spin change in magnetic materials, fundamentals of chemical reactivity. If we are able to look at this, we can move to the whole range of applications. Again, going to fundamental reaction dynamics, we look at coupling between various degrees of freedom. And here we need soft X-rays to probe, for example, photochemistry of DNA here. And we need element and site-specific probing. And then we also want to combine this with hard X-rays, such as, again, iron is always a really good example in this area. So iron trees by pyridyl, where you have a very complex dynamics, cascade of spin-orbit states, and you can probe it with hard X-rays, but then you can combine this with soft X-rays, and you can probe, for example, intercalation of metal complexes into DNA. And other areas, including fundamental photochemistry, reaction mechanisms, photoprotection, DNA damage, free radicals, anything you can think of, and anything we haven't thought of, which is called here your science. So if you haven't done XFELs yet, you should. So another example is, again, correlated spin and structural dynamics. And here you have an example of iron center in myoglobin and how this is functioning. And another one, again, in proteins is sulfur-sulfur bonding in proteins. So it starts from model systems, which have been done relatively recently, or rather, well, quite recently. But it would be really amazing to look at dynamics of sulfur-sulfur bond formation and breaking in proteins, because that's obviously very important. So again, if we are going back to the movie, we have ligand dissociation in primary steps, this time in protein dynamics. Of course, Fanny mentioned this after Alan's talk. But the applications then move to enzyme catalysis from chemistry perspective, photoprotection, drug target, and again, your science. So what do we need for next steps? We need to follow formation and breaking of hydrogen bonds, changes of electron density on the ligands, and we need high sensitivity, high rep rates, and multiple detection methods. So if I move to photocatalysis, it's a periodic table of X-rays, but sometimes we also call it periodic table of photocatalysis. So you have various atoms participating in various aspects of photocatalytic cycles, and therefore we should be able to probe all of them at the same time. Example here is binuclear complex in homogeneous catalysis, and the work was done, very beautiful work on simultaneous probing of two metals. So it's K-alpha emission from ruthenium and from cobalt here to understand really charge and energy transfer dynamics. Another thing that can be done is control of catalytic reactions. And this example is the controlling of catalysis with terahertz excitation. And that's exactly where multiple beams need to come together to the same sample to be able to achieve this absolutely amazing new direction of research. And so we need to combine X-ray with IR and terahertz excitation and detection, and we need to look for low energy reaction coding. Another interesting aspect is combine X-rays with electron beams, because that will give us aspects of pulse radiolysis, which we used to do at Dasbury, but to be able to do it at a very fast time scale, it will give you unique access to charged reaction intermediates. And again, combined methods, all of these abbreviations of hard X-ray, soft X-ray, UV, IR, terahertz, multidimensional, multicolor, anything. We want to get, ideally, everything about the sample in one snapshot. So moving to energy materials, again, the same questions, dynamics and simultaneous interrogation of different elements in light harvesting, in singlet fission, and that's a basic cartoon of simultaneous detection, but hopefully we can add many more to it. So simultaneous detection of different ages and different components. If we're moving further on, then again, we have spectroscopy and scattering on ultra-fast timescales, and we could use it to understand chemical activation, including with terahertz. Here is absolutely fantastic example of when you have terahertz pulse, which changes paraelectric to ferroelectric properties of your material. So can we actually interrogate this? Can we induce it and understand what is happening to our sample? And now we're actually moving into space, well, almost. We move to aerosols, atmosphere, space, combustion, and corrosion. And again, I don't repeat myself every time, right? Only every other time. We need high repetition rate, high flux, and combined spectroscopy and scattering, and some other parameters, which again, Alan already mentioned, to be able to look, for example, at such a fantastic process as nucleation and growth, where you go from inhomogeneous mixture to some seeding to some arranged structures. Electron beams, I've already mentioned, are really important in understanding corrosion and nuclear waste. And if we are able to combine X-rays with electron beams, then we will have this unique access to charged species, and we will understand better what is happening with corrosion. Again, you can consider storage of nuclear waste chemistry in a challenging environment. So we have corrosion, then there is also combustion and atmospheric space science, and you all consider them as challenging environments, and you go from solid to interface to liquid to gas. And in all of this, you can consider, well, what's in common between corrosion and combustion? Well, you have spatial and temporal inhomogeneity, complex energy landscape, and localized rare events which drive chemical change. And to interrogate all of this, and understand what's happening with spin, structure, and electronic changes, you need really powerful, really fast, really tunable X-ray pulses. A very quick slide on link with biology, mechanism of light-driven therapies. I already mentioned maybe intercalators in DNA and drug-target interactions. So there are questions that can only be tackled by femtosecond structural methods, and some of them started being tackled, like oscillator enzyme dynamics, by two-dimensional IR. But what we really want is X-rays, which would tell us these dynamics, structural dynamics in real time, or if we are putting our photosensitizer, which kills cells, into tissues, into 3D models, for example, we want to understand not only the end result, which we know, but we want to understand the mechanism of function. So it's important to consider sample delivery, energies, rep rates, and so on and so on. But there's also something that's been chopped off my slide, which is probably because it's telling me something, it's too much. But I just wanted to make the point of bringing together emission imaging and potentially X-ray imaging, because complementary to emission lifetime imaging, that would be really fantastic to have interrogation by X-ray imaging methods as well. This was just a slide to illustrate that we really all need to collaborate, because that paper had 20 authors, 15 affiliations in 6 countries. And this is my final slide to say, we want a real-time movie. We want to look at electronic spin structural dynamics. We want to be able to have multiple pumps, multiple probes. And the game changer here, at least from our perspective, is to combine X-rays and electron beam and various other energies, pulses of energy, mix and match, multicolor, multi-parameter space. So many thanks, and hopefully I've convinced you.